So, welcome to the pre recording of lecture 4 of MCS 320. So, in this second part of the second session, we are going to look at rational approximations. And we have already seen how to make a rational approximation, and we defined precision and accuracy already. So we can make approximations with a prescribed accuracy, but that's actually not yet the same as asking what is the next best rational approximation. So with the slides, I would like to introduce continued fractions, give the mathematical definition. Okay, but first, what are we looking at? So we are doing symbolic computation, and that means that we compute with symbols and expressions. It also implies that we try to compute with exact arithmetic, exactly as long as possible, and delay the use of numerical approximations. So one way how to keep working exactly is to use rational arithmetic. And this allows for exact computations. So if one works with approximations, then one can do this numerically using a floating point number systems, or one can do this also symbolically. So here you see two different approximations for pi. So this course is on symbolic computation, but I want to kind of situate this course in what follows next. In numerical analysis, we compute with numerical approximations using floating point arithmetic, and there we worry about error propagation. Now, symbolic computation, we don't have those worries, but there is another problem, and that is expression swell. And we will encounter expression swell, and actually already see this in this lecture. Okay, if you want to compute approximation to, let's say, pi of a prescribed accuracy, then you can take the following steps. So you evaluate the symbol that represents pi in a number system of a given fixed precision, and then one can convert this evaluated symbol into a rational number. So here is an example. If we evaluate pi to 5 decimal places, so here you see 5 decimals, the 3.1415 that we would see is truncated, so the 6 here at the end comes from rounding. Then if we compute a rational approximation, we find the 355 over 113. Now, if you are, depends on what perspective you take, the rational approximation is an exact representation, but still an approximation. It also actually occupies more space than the floating point approximation, already in this very limited accuracy of 5 decimal places. Okay, so what is the alternative to building rational approximations with the scheme as before? Well, we can work with continued fractions. So the word continued is probably here apparent with the dot, dot, dot. So we have a fraction that actually can go on forever. But here this fraction is defined by a list of natural numbers. And actually the last number better not be 0, otherwise it wouldn't really be defined. Now, if we have this continued fraction, then we can evaluate, so we can compute the rational approximation for all the intermediate numbers in this list. And the rational numbers that are obtained in this way are called the convergents. Now it seems rather cumbersome, but here is something quite interesting. So the continued fraction of the square root of 2 is extremely irregular. Actually, it's 1, 2, and then everything else is 2, up to infinity. So in a way, if you would look at the decimal expansion of the square root of 2, there would not be that much regularity, or certainly not that much, as much as you find from the continued fraction. So if we look at five numbers in that list, then this defines the convergent that is here written explicitly, and that evaluates to 41 over 29. Okay, what does this give us? Well, in case of the square root of 2, if we want now the next best rational approximation, we just go one step, we just continue one step in this continued fraction. So this is demonstrated here. So we have the convergence for the first 5 rational approximations. So these are now the first 5 best rational approximations that you can make. So the convergence give you rational approximations of increasing accuracy. So the slide ends here with the list of convergence for pi, and you actually see the 22 over 7 there, and you see the increasing length of the numerator and the denominator. So working with exact rational arithmetic will lead also to larger and larger numbers and an increased complexity. Okay, so this is the first short part of what I want to say with this lecture. Let me now switch to the Jupyter notebook to demonstrate how this works. So I have a notebook prepared, but let me demonstrate how to make it. So this is our Jupyter notebook for this lecture. So in lecture 4 we demonstrate rational approximations of prescribed accuracy and continued fractions. Again, before I continue, I should not forget to give this a proper name. So this is the course MCS 320, and I'm using this notebook during my pre-recording. So the first part is a repetition of what we have seen before already. So we will construct rational approximations of prescribed accuracy. So, and how do we do that again? Well, let me write down the 2 steps. So to compute a rational approximation with, say, p decimal places of accuracy, we do the following. So we've seen this before, but here I want to illustrate how to use restructured text to define an enumeration. So we evaluate the symbol. So let's say pi now, or square root of 2, in a number system of precision p, or higher if you want to be a little bit more careful, but p is fine. And then we convert the evaluated symbol, so now it's a floating point number, into a rational number. Here is an example. So compute an approximation for pi accurate with 13 decimal places. Or we are the 15th tomorrow, so the day of the lecture. So I do the two steps all at once. So this gives me an approximation for pi, which is going to be accurate up to 15 decimal places. And one can compute a sequence like this using a list comprehension. So we demonstrated this before. So this is not the same as the next best approximation. So let me illustrate this now with the continued fractions. So continued fraction gives rational approximations that can be considered as the next best so let me illustrate this with the square root of 2. I told you on the slides that the square root of 2 gives a very regular continued fraction. So here you see the continued fraction representation for the square root of 2. So the show command is actually here now a very useful thing. Okay, so then how do we get now to the next best? How do we get to the sequence of rational approximations? Well, we compute the convergence of this continued fraction. So in order to get the sequence of consecutive rational approximations, we compute the convergence of the continued fraction C from above. Okay, C dot convergence. And here you see something very interesting. We get what is called a lazy list. So we have our continued fraction of the square root of 2. We see that 1 is the first approximation, 3 halves. So you can see the 1 plus 1 half, that's the next best rational approximation. And then we have the 7 fifths. But after that, and here you see that Sage Math is rather lazy, it kind of stops. Okay, how can you now see the list? So the laziness is related to the delayed evaluation. So what the convergence actually does, it gives us almost an algorithm. So an algorithm that is going to be evaluated whenever the user wants it. So let us compute the first 8 convergence. So we only see the first 3. So how do we do this? I'm going to assign the convergence to a variable name. And then I need the first 8, so I can leave off the beginning. And I'm going to convert this to a list. And I'm going to still do something with that list. Okay. Here we go. So you see, I do have a list now of 8 numbers, and the 8 numbers get larger and larger. Well, the numerator and the denominator gets larger. So the numbers themselves, the values, actually converge to the square root of 2. Okay, so this is actually now an increasing sequence. Well, in a sequence, so let me document this. So the convergence are a sequence of rational approximations of increasing accuracy. Now, you don't need to believe me for that. Let me compute the relative error. So I first will compute the relative error for the last point, a number. So let me compute, let us verify this. The accuracy of the last number in the list. So what's the error there? So the error is the absolute value of the square root of 2 minus the last number. Note that we are starting to count from 0. So we have this error now. So in here you see kind of interesting. So this is what Sage does to us. So it computes the exact relative error. I want to see the scientific notation. So let me go to the scientific notation, doing some Python. So it looks very technical, and actually converting to a double with RR might be just much shorter, but I like to show you some Python constructions. So here you see that the error in scientific notation is 10 to the power minus 6. So I have about 6 decimal places correct. So this is different from the previous construction. I start with 6 decimal places. So let's verify this. So I can do the square root of 2 digits equals 6, and I have to do this in the n. So you see that this is a longer number. So I actually don't really have so let me document this. So this is again a side step. So observe the difference with the approximation of a prescribed accuracy of 6 decimal places. Alright, so I want to do this now for all. So let me, for all the numbers in the sequence here. So here I have the sequence L, and I want to apply this formula. So I can copy and paste, and make a list comprehension with this. So let me first define what I want to do here. We can compute in one single instruction, we can compute the accuracies of the convergence in one single instruction. So list comprehensions are very, very useful. So here I have it for the 7th one. I replace the 7th by k, or actually I can do better. I can replace this by for x in L. So I can do that. So let me see if that is going to run. So here you have it. But that's not so useful yet. So, but it shows the formula. So what I want is the scientific notation. So I want the expansion and there is a typo. Here you see the list of the errors, and indeed the accuracies, they actually increase. So we know here the error of the 3rd one is exactly 10 to the power minus 2. But you see that actually there are it goes up more gradually than you would have with the prescribed accuracies. So let me document this. This list of relative errors shows that the progression is of the approximations is slower than the list of rational approximations with prescribed accuracy. Okay, so this 4th lecture is done at quiz time, so that's why I will finish also here rather soon. Let me make the last computation for pi. So on the slides, let us compute the convergence for pi. So the first 10 convergence for pi. So how do we do this? We first make our continued fraction, so call it c pi, the continued fraction for pi. Then I have the convergence for pi. And then I have the list, the first 10 that I convert into a list. And here you see. Voila. So normally we try to do this step by step, but if you are quite sure about what you want to do, you can put everything in one block. And here you see the consecutive approximations, the consecutive rational approximations defined from the continued fraction. So each number in the list is essentially the next best rational approximation, follows one more term in this continued fraction. Okay, with this I conclude. One last thing is that I want to clean up things a little bit. I would also recommend that you do this practice. So I will, of course, before try to save it. Then you interrupt the kernel. So although you restart everything, you clear all the output. And then we run all the cells once the kernel is ready. And this kind of summarizes the 9 instructions that we executed in this session. Okay, so this concludes this session. Thank you for your interest